1900, physics seemed largely complete. Maxwell's equations had established that light and thermal radiation propagate through space as continuous electromagnetic waves, with energy distributed across smooth, unbroken fields. To study how materials emit this radiation, physicists use the theoretical model of a blackbody, an object that perfectly absorbs and emits all electromagnetic radiation. According to classical theory, the spectrum of emitted light from a blackbody depends entirely on its absolute temperature. This chart displays the experimental reality of that thermal radiation. We are looking at the intensity of emitted light plotted against its wavelength for a blackbody at various temperatures. Notice the distinct peaks on the graph. As the temperature of the blackbody increases, moving from the 3000 Kelvin curve up to the 6000 Kelvin curve, the peak intensity of the radiation grows and shifts precisely toward shorter wavelengths. Physicists attempted to derive these exact curves using classical statistical mechanics and Maxwell's wave theory. This effort resulted in the Rayleigh-Jeans law. But when applied to the graph, the Rayleigh-Jeans law fails. While the math matches at long wavelengths, as wavelength decreases toward the ultraviolet range, the classical prediction shoots straight upward. It predicts a black body should emit infinite energy at short wavelengths. This divergence, the ultraviolet catastrophe, provided mathematical proof that treating energy transfer as a continuous, infinitely divisible wave was incorrect at the microscopic level. In late 1900, German physicist Max Planck found a way to force the mathematics to fit the experimental data, but it required an assumption that broke classical rules. Planck hypothesized that the atomic oscillators within the walls of the black body could not emit or absorb energy in a continuous flow. Instead, their energy had to be restricted to discrete integer multiples, defined by the equation E equals n times h times f. By restricting energy to these discrete packets, high-frequency oscillations suddenly require large, indivisible chunks of energy. At thermal equilibrium, the probability of an oscillator acquiring enough energy to emit these massive high-frequency packets is extremely low, preventing the infinite divergence seen in the classical model. When you integrate Planck's new radiation formula across all possible frequencies, the total energy density does not explode to infinity. The integral resolves to a finite value, proportional to the fourth power of the temperature. This derived integral matches the Stefan-Boltzmann law, an experimentally proven rule stating that the total radiant power emitted from a surface is proportional to the fourth power of its absolute temperature. Yet Planck did not believe he had uncovered the physical nature of light. He considered his constant h to be a purely mathematical trick, a necessary adjustment to make the thermodynamics function, while assuming the radiation itself still traveled through space as continuous waves. Planck successfully fixed the equations for thermal radiation, but the actual physical reality of the quantum remained a controversial hypothesis. It would take a direct analysis of light-matter interactions to determine if energy was truly broken into discrete chunks. The definitive test for the physical nature of light came from an entirely different phenomenon, the photoelectric effect. This diagram illustrates the experimental apparatus. Monochromatic light enters an evacuated glass tube through a quartz window and strikes a metal photocathode. This impact ejects electrons from the metal, sending them across a vacuum gap to an anode and establishing a measurable photocurrent. By adjusting the connected battery, researchers can apply a negative voltage to the anode. When this negative voltage is dialed up just enough to repel even the fastest-moving electrons and drop the current to zero, we record the stopping potential, V0. This metric gives us the exact maximum kinetic energy of the ejected electrons. When classical physicists analyzed the data from this apparatus, their continuous wave theory failed in three distinct ways. First was the intensity problem. Classical wave theory predicts that a brighter, more intense light should impart more kinetic energy to the electrons. In reality, higher intensity only ejects a higher number of electrons. Their maximum kinetic energy remains constant. Second was the frequency problem. The experiments revealed a strict threshold frequency. If the incident light is below a specific frequency, 0 electrons are emitted, regardless of how intense the light source is. Finally, there was the time delay problem. Classical physics predicts that a very thin light wave would take time to pool enough continuous energy to dislodge an electron. In reality, the electron emission is instantaneous. Continuous electromagnetic waves fail to account for the data. A wave cannot explain a process that is threshold-dependent and entirely indifferent to light intensity. In 1905, Albert Einstein proposed that light propagates not as spreading waves, but as a stream of indivisible energy packets called photons, each carrying an energy equal to Planck's constant times its frequency. Einstein formalized this into the photoelectric equation. The energy of the incoming photon, hf, equals the work function of the metal plus the maximum kinetic energy of the ejected electron. The work function represents the minimum binding energy keeping the electron attached to that specific metal. This particle model explains why there is no time delay. A single photon collides with an electron, transferring its energy in one indivisible moment. If the photon's total energy is lower than the metal's work function, it cannot dislodge the electron, regardless of light intensity. We can map Einstein's equation directly onto the experimental data. This chart plots the measured stopping potential against the frequency of the incident light for 3 different metals: cesium, sodium, and calcium. Notice the x-intercepts. Each metal has a unique point where the line crosses the axes. These points represent the threshold frequencies for each specific material, below which kinetic energy drops to 0 and no emission occurs. But the most critical feature is the slope of these lines. Despite the metals having completely different binding energies, all 3 lines are parallel. The slope is exactly equal to Planck's constant divided by the charge of an electron. The experimental slope of these lines precisely derives the same value Planck used for blackbody radiation, establishing h as the universal physical constant governing all light-matter interactions. Even with Einstein's success, a theoretical hurdle remained. If the photon is a true particle, it must exert physical momentum upon impact, yet photons have 0 resting mass. In 1923, Arthur Compton designed an experiment firing highly energetic X-rays into materials with loosely bound valence electrons to measure for physical momentum transfer. This diagram captures the mechanics of Compton's collision. The incident X-ray photon strikes the electron and ejects it. Crucially, the photon itself recoils, scattering away at a measurable angle of deflection, marked here as theta. During the impact, the photon transfers a portion of its kinetic energy to the recoiling electron. Because the energy of a photon dictates its wavelength, losing energy means the scattered photon must emerge with a longer wavelength than it started with. This increase is known as the Compton shift. We can see the shift directly in Compton's intensity distribution charts. Look at the primary peak of the incident radiation at 0 degrees. As the physical scattering angle of the detector increases from 45 to 135 degrees, the wavelength of the scattered photon distinctly shifts to the right. The magnitude of this wavelength shift obeys the laws of conservation of momentum. Despite having no mass, the photon imparts momentum equal to Planck's constant divided by its wavelength, acting exactly like billiard balls colliding. Compton's scattering data eliminated the last defense of a purely wave-based model. Light acts as a quantum entity, possessing both localized energy and measurable physical momentum. If massless light waves act like localized particles with physical momentum, do massive, solid particles behave like waves? In 1924, Louis de Broglie proposed that wave-particle duality extends to all matter. He used the equation lambda equals h over p to link the physical momentum of any particle directly to a specific wavelength. We don't see baseballs rippling like waves because Planck's constant is incredibly small. For objects with macroscopic mass, the resulting wavelength is too minuscule to observe. But at the scale of an electron, this matter wave dictates the architecture of the atom. This diagram applies de Broglie's wave hypothesis to the Bohr model of the atom. You are looking at a visualization of electron waves mapped onto the first 3 orbital paths. For an electron's orbit to be stable, the circumference of that orbit must perfectly accommodate an integer number of electron wavelengths. The wave must cleanly close in on itself to create a standing resonance, explaining why electrons are restricted to discrete quantized energy levels. Matter is not constructed from tiny, solid, point-like spheres. The discrete architecture of the atom exists because massive particles exhibit wave phenomena. This leaves us with a final contradiction. A wave spreads out over space, while a particle exists at a specific point. How can an electron have a measurable wavelength, yet still strike a detector with a localized physical impact. If we describe a particle using a single infinite plane wave with one perfectly defined wavelength, we have zero information about where that particle actually is. It is equally likely to be anywhere along the axis. Quantum mechanics resolves this through the wave packet. A particle is described by a superposition of multiple waves, each with slightly different wavelengths and momenta. When these differing waves combine, they undergo constructive and destructive interference. They cancel each other out across most of space, adding together only in one specific region to create a distinct, localized pulse. Although this packet is localized, it is still a wave. In quantum mechanics, we find that the strength of this wave, its squared amplitude, predicts the likelihood of finding the particle at a specific location during an experiment. This model replaces classical certainty with a localized distribution of likelihood. The physical behavior of every electron and photon is defined by these wave packets, where the scale of their interactions is determined entirely by Planck's constant.